Hello everybody. In this video we will have a brief introductions to thiols and thioethers. So thiols are basically sulfur analogs of alcohol. So if you noticed, your sulfur is right under the oxygen in the periodic table. So if we replace the oxygen and replace this with sulfur, we will get our thiols. And same thing with ether. So ether is the oxygen version of the compound where oxygen is connected with two carbon chain on either side. Here in thioether, this is also called as sulfides. So either one naming is fine. So I like to call thioether because then you can correlate with ether. The thioether, the sulfur analog of ether where oxygen is replaced by sulfur. Let's do a couple of key properties of thiols. So thiols are more acidic. So if you compare thiol versus an alcohol, so the pKa of this compound is around 15.7. pKa of our thiols are around 10.5, if I remember correctly. So obviously this one is more acidic. So if this one is more acidic, so this one is more acidic. Well, why this is more acidic? Well, just by looking at the pKa value, we can say that 10.5 is smaller than 15.7 and lower the pKa, more acidic it is. But let's try to rationalize this. So what happens when you deprotonate this? So you can deprotonate this. Let's say we deprotonate this. So what is the conjugate base of this thing? The conjugate base is you bite a proton out. This acidic proton is gone. So what's left over? The leftover is CH3S minus. So this negative charge is delocalized across a larger atom. So sulfur atom is larger. So this atom is larger. So the negative charge is being delocalized, dispersed across a larger atom. So as a result, this base here, this conjugate base is a lot more stable. And we know that when conjugate base is more stable, the corresponding acid is going to be more likely to be deprotonated. On the opposite side, we have CH3O minus. Okay, so this conjugate base would be a little bit more stable. Also, it depends on the because we are discussing everything in water. Okay, so what if we treat this one with a base OH minus, and then the product would be water. And this equilibrium reactions, what is the pKa of water? pKa of water is 15.7. So we know that if two things are in equilibrium, two acids are in equilibrium, so there is an acid here, there is an acid here. If two acids are equilibrium, the equilibrium is always going to be biased towards the weaker acid. So the water is our weaker acid. So the equilibrium is always going to push towards the weaker acid. So you can see the arrow is more towards the weaker acid. All right, so let's move on to some reactions. Again, thiols are a very important class of compounds. So you can have something like this, CH3SH, and you treat them with OH minus, and then you make with CH3S minus. And this would serve as a good nucleophile. And when you treat this with something like CH3I, you can have an SN2 attack here. So this is an SN2 attack. Remember, SN2 attack inverts the stereochemistry if there is a stereocenters, and it can only happen with primary and secondary. So let's say we have an SN2 attack here. What is the product going to be? So your product is going to be CH3S, and there will be another CH3 here. Okay. All right. So now this CH3, we could do more reactions. So this is your thioether. This thioether actually can do a lot more reactions that our original ether couldn't have done. So let's say we have react with another CH3 here. So CH3I. And this can do another SN2 attack. So the lone pair on thioether could do this. So CH3S, CH3, CH3. Just like oxygen, when sulfur makes 3 bonds, it should have a positive charge. So this is called sulfonium ions. Sulfonium ions. The sulfonium ions are very good source of methylations. So here is why. So just like we did with the oxygens, every time you have a positive charge on sulfur, what is your goal should be? Your goal should be to neutralize, right? So we could do something if we have a very good nucleophile. If we have a nucleophile, this nucleophile could take out the methyl group. So nucleophile can take out a methyl group. It's good for methyl group. It doesn't do very well if you have a bulky alkyl group right there. So it's try to get the methyl group first, then maybe sometimes secondary, but if it's too big, then it's probably not going to happen. This is a biologically very relevant reactions. I will show you in a second why. So the product of these things would be CH3S, CH3. Okay, and then what's the leftover? So this is nucleophile with CH3. Now this reaction is the most important one I'm trying to highlight. This is a biologically very relevant reactions. So this is called methylation reactions. So this reaction is called methylation reactions. So in our body, we have something called SAM. Not the Sam and Frodo from Lord of the Rings. It's called S-adenosyl methionine. So it is a methionine derivative. It's called S. Hopefully my spellings are correct. Methionine. So this one is a methylating reagent. So methylating agent. So this is a very common methylating agent in our body, in our cells, in our cell. Okay, so what it does is, so SAM, just like here, the sulfonium ions right here, you see, it has a sulfur. So this sulfur is part of methionine amino acid. So when we come to biochemistry class, you will see the structure of methionine. But the point here is it has a methyl group, and on this side a big group, on this side a big group. So that's on this side you will see methionine amino acids, and on this side you will see the nucleoside adenosine. Okay, so as a result, so when sulfur has 3 bonds, it's gonna be plus charge. Now we could use this methyl group just like we did in our lab. So that's how our body does. So now you can have a nucleophile, and that's how you methylate our DNAs and bunch of agents. So we could basically methylate anything we want in our body. Okay, and then we get our methylated nucleophile. Okay, and that's gonna, you gotta regenerate again the SAMs. So that's the biological relevant reactions. Another thing that you want to see is biological reactions is we have something amino acids. This is cysteine amino acids. 2 cysteines can combine to make something called disulfide linkage. So I will draw another cysteine. Cysteine is a thiol, right? So this is your thiol. Just know all the thiol containing compounds are stinky compounds. They smells pretty bad. So you can make disulfide linkage from here. Two cysteines can oxidize. So when you remove the hydrogen, so these two cysteine can oxidize to make disulfide linkage. We'll go over in detail in our biochemistry lectures, but I'm just saying this for now. All right, so this is our oxidation reactions to make disulfide linkage. So this is disulfide links between two cysteine. Okay, so this was cysteine. This is also cysteine. And two cysteines oxidize or combine, whatever you want to call. You can also go backward direction. So you can break this disulfide linkage by adding hydrogen. So that process obviously called reductions. So reduced to go backward. So you can do any of this reaction. So this is very important. Without this reactions, you will not survive. And I will explain in our biochemistry lecture why. All right, so that's pretty much all, a brief introductions to thiols and thioethers. Again, there is two key idea that you should focus, that usually thiols are a lot more acidic, and we can serve them as nucleophiles to do SN2 reactions with an alkyl halides like CH3I or CH3Br. And then we can create a sulfonium ions from there. You can do a bunch of other oxidation reactions to make sulfoxide as well. So let's not worry about those. And we focus on this methylation aspect of our study. Okay, let's stop here.